Aaron's up next here to talk about an open Snowflake camera for research and education. So take it away, Aaron.
Thanks. Is everything showing up okay?
Yep, looks good.
Thank goodness, because Microsoft Teams bit the bullet earlier today, had to reinstall. I'm glad it's working. Yeah, so this is great. Segue from the previous talk. So I'm not a business, and the question is, if I'm designing open hardware, how can I get this in the hands of people, but still have a lot of same problems? Like, what about support? Do I have endless time to provide support? I'm willing to provide support, but if it took off, I'd probably get myself in trouble. And so I don't know if this figure was shown earlier. I saw it in the Slack channel earlier, and I missed yesterday because of instrument stuff. But if you think about where open hardware falls into this picture, it hinders a lot of things. And so what I did is I shaded in this area about accessibility and inclusiveness, because anytime you add material items that cost money, just by its nature, you're going to decrease accessibility, and then that's going to perhaps lead to reduced DEI. And I think of situations like myself where I'm at a non-R1, so maybe we don't have as much resources as R1, but I've also worked a lot with primary undergraduate institutions and tribal colleges, which have even less resources. And so it could be a struggle just to get equipment, let alone be able to have the skill sets to work with it, because they may not have the support you normally have with like a commercial instrumentation. And so for my project, there's really nothing new about this instrument that I've developed. I'm just reinventing the wheel. And so a lot of my research is dedicated towards understanding processes between falling and blowing snow. And historically, imaging snowflakes or other types of precipitation is difficult and expensive. You can look at studies where basically aircraft probes are repurposed. And, aircraft probe, you're easily looking at 6 figures. And even for ground-based imagers, they're easily 5 figures, and many of them are closer to 6 figures than on the lower end of the spectrum. So they're expensive. And also, a lot of the instrument design hasn't really been focused on what do they do in environments where wind's a problem. And so I started this project just with a couple basic things I wanted to accomplish. I wanted to make an instrument that would work in windy environments. I wanted it to be more affordable, which just by that nature would make it more accessible. I wanted the software and the hardware for it to be open. And the only way to really get that affordability is to use off-the-shelf items and 3D print the other parts. And we saw a mention of 3D printing in the last talk. And so the idea is, if you get this stuff at a low enough cost, you make everything open, then that should open the doors to having more instrumentation in the classroom. So if you're teaching cloud physics, you can put this instrument out in the open, have students collect data and tell us what's happening, and also have more instruments. And so if you think about where we typically have microphysical instruments, they're limited to field campaigns, select sites, and man, it would be great to have networks of these instruments. You can put them underneath the area where you have radar coverage and know what's happening in like every single county in, say, the state of North Dakota or whatever. And so with that, I introduced OSCRE, the Open Snowflake Camera for Research and Education. Effectively, what this is like an open designed hydrometeor imager. And so it's not closed like, say, a multi-angle snowflake camera. There's just one camera, for now, one light. And what I've done is I've used off-the-shelf components and put the camera and the lens and the computer in one housing, the one on the left. And then the other side is a strobed LED light. And so that strobe light will allow us to basically image regardless of what the wind is doing. And throughout the process of making this instrument, I try to make decisions that would facilitate open design and also accessibility. I'm using basic machine vision cameras. There's a whole industry built around these things. I tried to pick a model that has like an open SDK, has stuff like a Python backend for it, so you can develop software easily. Has an easy interface. So if you get into some of the more fancy machine vision cameras, they use all sorts of fancy links between computer and camera that makes things more expensive. And so I'm just using something that uses USB 3. I think everyone has experience with that interface. The other challenge is when you get down in the machine vision, a big challenge is your lens good enough for the sensor you're putting behind it? And so I picked a camera lens that you could basically go to the camera store and purchase. What ends up happening is, because this lens is developed for large cameras, pretty much any machine vision camera you put in front of it's going to outperform the sensor itself. And so You can get these lenses for any sort of type of camera. In fact, if you're a photographer, you may have one of these laying around. You can throw this in front of the camera and start getting snowflake images. And another advantage of using this type of lens on this camera is it gives you a very high crop factor or telephoto effect. In other words, you're going to see smaller particles, and snowflakes tend to be small. And so at the end of the day, I don't want to focus too much on the resolution, but it's adaptable depending on what sort of focal distance you have. But we end up with basically resolving particles down to about 50 microns or so with the current system. On the computer side, it's important to note that the software for the camera it can be run on all operating systems, and they have a Python version of it. But I wanted to basically make the computer portable, something that is contained within the system, so you don't need a large desktop computer to drive it. And on that end, I'm using a small NVIDIA Jetson board. And so this is basically an ARM CPU with NVIDIA GPU. It runs Ubuntu. These are designed for machine vision applications. There's all sorts of folks putting these on like robots and like doing ID of things in real time. And this was something that made sense when I started the project. It still makes sense. The problem is, and one of these challenges that you didn't foresee was the chip shortage, and that tied to COVID and other factors. And so the problem is the way I've currently designed this, you can't even get these boards right now, at least not at an affordable price. You basically have to buy them off the black market for like 5 times what they originally cost. And so something I'm working towards the future is, coming up with carrier boards for these chips that are attainable, are not that expensive. So if someone wants to build this thing, they can actually get the parts, because that's a big part of the open hardware is, can you actually get the pieces you need for the system? For the lighting, I'm using strobed LED lights. And so what happens behind the scenes is the software tells the camera, like the chipset on the camera, to say, hey, send a pulse to the lighting, trigger the lighting at a specific duration. And so I'm commonly operating these things down to about 5-10 microseconds or so. And in other words, it doesn't matter if you're in a blizzard or if it's calm weather, you're going to be able to get nice, sharp, focused images of snowflakes. One thing to note is they are strobe lights, and so if you have anyone with light sensitivities, you have to watch out around these things. But overall, it's a much more elegant solution than constant lighting because it takes a lot less power, and you can actually use lenses on these type of lights to define the sampling volume. So something I'm working on right now is basically putting patterns in front of the light and the lens, and basically defining what the sampling volume is. And so with any sort of high meter imager that's camera based, you have problems with depth of field and what's in focus, what's out of focus. That changes the sampling volume. That impacts what your actual number concentration is. And so the idea is, hey, if we can just define the lighted volume, then we don't have to worry about the focus stuff. It'd basically be confined to the stuff we know is in focus. Putting it all together, so we heard about 3D printing earlier. That's really where we save a lot of the money. Instead of having to get parts machined by a company, I can go in and use like OpenSCAD, generate 3D parts, 3D printed parts. The nice thing is you don't really need expensive printers to do this. Like the first prototypes I was using like a $200 Ender 3 printer. I'm now using like Prusa stuff because I think the quality is a little bit better. But in the scheme of things, the ability for any sort of institution to have a 3D printer, it's not really a price barrier anymore. Now, whether folks there have the knowledge and expertise to print it, that's a different thing. But the ease of 3D printing it's become a lot easier to do this in recent years. So I'm not going to focus on all these specifics, but overall, if you use what I would say the science quality version of OSCRE, where you have like defined lighting and whatnot, you're sitting about $5,000. If we go to an affordable OSCRE, which is basically you're going to get pictures of snowflakes, they're not always going to be in focus or whatever because the depth of field is narrower or whatnot, you're still down about $3,000. And so that, if anyone has looked at costs of other high meter imagers out there that are commercialized, this is way, 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 way cheaper than those other options. So here's just some examples from OSCRE. On the left-hand side, we see some composite images of various types of snowflake images or snowflake events. You see examples of aggregates. You can tell how much rhyming is on them. One of the surprises that I was happy with is you get a lot of nice detail in mixed precipitation events. So you can see basically the transition from liquid drops, where all you get is like internal reflection of the light through the water droplet, to various states of being frozen where it becomes more opaque. We've imaged grapple of various stages of melting. And what's happened is we've actually used this to identify problems with other instruments. And so one of the common disdrometers out there that's used today is the Parseval from Hydromet. Great instrument. However, we noted problems during blowing snow events. And so what we did is we looked at the particle size distributions from OSCRE, compared it to these distributions we thought looked wonky from the Parseval. And it turns out that just one of the current limitations of the Parseval design is in blowing snow events, there's too many particles in that sampling volume, and the instrument ends up thinking there's very large particles in there. And so we're already doing some nice work with OSCRE. Some other examples, the sampling volume is a lot larger compared to many instruments. So if we're looking at blowing snow events, you can actually end up with hundreds and hundreds of snowflakes or shattered snowflakes in an individual image. You can see an example of a pristine hexagonal plate in here, but then various other shattered crystals. This was actually an image from the first winter I built this, where we had poor lighting. And so in the new revisions to the instrument, you'll have a lot less of this issue with the out of focus particles. So right now, with the previous generations, it was mainly an image processing problem. And now we're trying to take that out. So it's much, much easier to identify the particles and know that they're in focus. Another thing to know is you can adapt this system to other types of precipitation. And so we happened to have a hail event just a couple weeks ago, and I was elated to see lots of hail coming down. Most of these hailstones around 1 centimeter or so. And it turns out that you can actually image hail with this thing. And so what you're seeing here is basically lighting is coming from the left-hand side of these pictures. And then from being outside in the hail, I can tell you what these hailstones looked like was basically dry growth surrounded by wet growth. And so this light was entering the wet growth, and then it was internally refracting and reflecting through it, hence these little dots you see here. And then the more opaque area, that's the dry growth of the hailstone. And so that suggests that maybe we could adapt this thing to warm season events, change the sampling volume, maybe adjust the lighting, and we could actually get information on hailstones. And that's part of the fun of open hardware, right? Is if you come up with a system where you can connect all the parts, people can modify this to fit other objectives. We've also done some comparisons of OSCRE against other hydrometer imagers. I'm running low on time, so I'm not going to elaborate on this much, other than we see pretty good agreement between the two. So we think we're on the right track. And so what's for the future? Well, upcoming plans is we're going to be deploying one, possibly two of these to Sail and Splash. And so one will be at the AMF2, that's for certain. Working with the NOAA folks to see if we might be able to get another one out at the Kettle Pond site. At the same time, we'll have two deployed in North Dakota, possibly more, depending on how many I can put together with the parts I can get, given all the chip shortages out there. And then we've got some stuff pending, trying to work on getting these into various classrooms and demonstrate the educational utilities of the instrument. There's even more work that can be done on the software side. Right now, the system is really underutilizing computers I'm using. We're just using the CPU to drive the camera, do basic image processing. But if anyone's been paying attention to the hydrometer imaging community, just a few days ago, this MaskDB database was released. And now we've got these databases that are open with millions and millions of different types of different snowflakes. And so the idea is we could use this to do some machine learning using like languages like TensorFlow, and that's designed to run on these Jetson boards. And so given the demos that are out there, I'm pretty optimistic that these small little computers will be able to do basic hydrometeor ID in real time. And just being able to discriminate whether it's snowing versus blowing snow would be a huge, huge benefit to our partners, such as the National Weather Service, who want to know what's happening on the ground. So with that, that's the whirlwind tour through OSCRE and some of the challenges and stuff I faced working with this hardware. Steve Kenny at Smart Vision Lights, that's our lighting guy. He's been instrumental in getting that stuff working, and the folks at Wilco Imaging. I think one of the challenges is from a science side, we're not making maze instruments. And so it was hard finding someone to listen to us from the commercial space, because frankly, they're not going to make money off us, right? And hopefully if this thing took off, then people would be buying a bunch of these lights or whatever, but we're not a high dollar customer. And so Steve actually, his daughter was actually an atmospheric scientist. And so I think he took a keen interest in this compared to maybe the typical people out there. So with that, I'll stop and I'll take any questions.
Great. We have probably time for one question if there's any out there.
I got a real quick one, Adam. Have you talked to Claire Peterson and the PIP folks, Aaron? Because it feels like to me there should be this effort for open source Snowflake analysis software that would be useful across many instruments.
Yeah, so that PIP was built partially with the support of Claire. The NOAA project is a joint thing between us and Norm Wood out at UW Madison, and Claire was there before she entered professorhood. So we have been talking a lot about this, and like the PIP right now. So I think I told Claire this, but that's how this instrument came to be. Is I wanted to get a PIP and I couldn't.
And you can't get them. You can't get them. Exactly.
Can't get 'em. And I don't feel like waiting around until I'm all completely gray. And I was like, I'm just gonna build my own. And luckily it worked out for the most part. But
very exciting.
You know, the PIP, the parts for the PIP are old and aging, and so
I think you might have just invented the new PIP, Aaron.
Well, so we've talked about, you know, this lighting manufacturer has, they also make backlights, and so there's no reason why I couldn't try and replicate the PIP format and see how it works. I don't think I have to worry about patent stuff anymore, but yeah, I don't know.
Okay, great. Thanks, Aaron.